Okay, it's going. Perfect.
Okay, so good morning, everyone, and a warm welcome to this ECEMP skills workshop. I'll just share my screen because I've got a presentation to start us off with. So my name is Will Usher. I'm an assistant professor at KTH Royal Institute of Technology, and I'm joined today by Trevor. Trevor, do you want to introduce yourself?
Hi everyone, I'm Trevor, and I'm visiting with Will for the last months.
Yeah, so it's been great to have Trevor working at KTH, and during that time we've been developing a paper on how to conduct global sensitivity analysis of an energy system model. The paper isn't ready yet, unfortunately, but we're hoping to submit it in the next couple of weeks. So this is maybe a little bit premature, but hopefully you'll get the main idea from this workshop. So before we get started, I thought it'd be good to know a bit more about who you are and what you want to get out of this session. So if you can join, I've set up a Mentimeter quiz, and you can join, go to menti.com and use this code. And I'll just switch to the other screen actually, where it should still be published, yeah. So if you go to menti.com and use this code and provide and then answer these questions. So the first question is, could you just give us a 1 or 2 word description of your current role? So what do you do? Are you a modeler? Are you a decision maker? So there's 14 people on the call so far. So I'll give you a couple of minutes just to load up the website and respond. And it should give us time for other people to join the session as well.
现在呢，最关键的这个生产要素大家知道是工业的血液，那就是石油啊。但是呢，到了说有血液的话，那就是应该我们的这个数据。但是数
Great. So thanks everyone. I think we'll move on to the next question. But I see we've got a good cohort of modelers here, researchers, project manager, someone looking at modeling activity. Okay. So the next question is, yeah, which of these methods are you familiar with? So this doesn't mean you've used them, but which of them have you? Okay. Unfortunately, I see this as a radio button, so you can only choose one. So which of these techniques are you most familiar with? Sorry, I didn't test that. Great. Okay. So the next, if you just joined the call, we're just starting off with this this quiz just to get us warmed up. You can go to menti.com and use this code at the top here, 46492930, and then you can join the quiz. And I'll make the results public at the end of the session. Okay, so let's move on. So the next question is, so which one of these methods have you implemented or used? And I guess, unfortunately, it's not multi-choice, but which have you used the most, I guess?
Will, you're muted.
Thank you. Yeah, so the final question is, what would you like to get out of today's session? And your responses will be shown on the screen here. So. Okay, this is really useful. Yep. So we'll provide an overview of sort of two different options. I guess a discussion of two typical ways of doing a sensitivity analysis. We'll be diving into how to implement a global sensitivity analysis. So you'll get a deeper understanding, I hope. We'll provide some good references of where to look next. And our forthcoming paper will definitely help with that as well. Yeah, this approach is definitely one that can be transferred to other models. And yeah, I think we'll cover most of these bases. Great. Okay. So the final question is, if you're comfortable with doing so and you'd like to be notified of the forthcoming paper, you can write your email, and I'll send you an email with the link when the paper comes out. But yeah, that's only if you're comfortable with doing so, of course. Okay, so I'll just leave that open and move back to the main presentation. Are there any questions or comments so far? Okay. So the way that today's session is going to be structured is I'll give a bit of a talk at the beginning just to give an introduction and the background to global sensitivity analysis. And then we'll get into some more practical work where you'll get your hands on. We're going to be working in a Jupyter notebook and playing with the sensitivity analysis parameters. And in the background, there's a very, very simple energy system model, which are based on the osmosis framework, which you'll be able to play with. So first, what is global sensitivity analysis? So probably the best definition is one provided by Saltali, who's a researcher who does a lot of work on, has written a lot of papers on and books on sensitivity analysis. So it's the study of how uncertainty in the output of a model can be apportioned to different sources of uncertainty in the model input. So basically, it's an approach embedded within uncertainty analysis, but it's different from uncertainty analysis. So an uncertainty analysis is when you propagate uncertainty through the model and you try and quantify the amount of uncertainty in an output. And sensitivity is different from that. Here you're trying to understand which of the inputs to the model influences the variation in the output. So you can think of it as sensitivity analysis identifying what are the main drivers of the model, if you like. So the word global means that all parameters are moved over their entire input ranges at the same time. And we'll get into why this is important a bit later. But probably the approach that you're most familiar with and what most people think of when they think of a sensitivity analysis is what's called a one-at-a-time sensitivity analysis. And this is when you've got your model results or you've done your modeling, and then you return to the model and you perturb one of the outputs or one of the inputs, sorry, say a fixed distance from the central value that you've been running the model at. And you only change one input at a time. So this gives you some insights, but they're limited. And again, we'll come up with an example, demonstrate an example of this later. And yeah, I've provided references, but Saltelli's written a good introduction to global sensitivity analysis. So why perform a global sensitivity analysis, and why is this sort of relevant for energy system modeling? Typically, we don't do an uncertainty analysis of an energy system model. We don't try and propagate probability distributions through an energy system model. That doesn't really make sense because many of the uncertain inputs we can't quantify in any meaningful way. But I think my main points are that global sensitivity analysis is really useful for a modeler, and it's really useful for the process of model development and understanding your model in a much deeper way. Typically, when you are modeling, you will get to know a model over time, how it behaves, and often that understanding is pretty good, but it's always sort of niggled me how that no one ever really knows. They don't really know how their model behaves, and that led me down a path of sort of investigating approaches to try and investigate formally then the behavior of models. And so global sensitivity analysis can help then in this endeavor of sort of interrogating your modeling. And typically, global sensitivity analysis can be used in 3 different ways. So we can use it to identify the key drivers of the model results, and this is the setting of factor prioritization. You can also use it to identify unimportant parameters, and that's factor fixing. So these are parameters or inputs to the model that don't actually do anything. They don't influence the results in any meaningful way. And another interesting approach is this factor mapping, and that's quite similar to scenario discovery. So where you identify an area of interest in the output of the model, and then link that to the values of the parameter of the input parameters that cause that effect, that desirable effect. So we're not going to talk about factor mapping today, but we are going to talk about factor prioritization and factor fixing. So I'm presenting this slide in reverse order, but so why are those sort of aspects of global sensitivity analysis interesting? Well, they're interesting because they can support our use of scenario analysis. So typically when we produce scenarios and are doing an energy system optimization study or to inform some type of energy planning. We'll develop a suite of scenarios, and we want to demonstrate sort of interesting parts of the model output space using those scenarios. And at the moment, all the existing approaches really just do this randomly or through the sort of intuition that the modeler has. We say, okay, I know that fossil fuel prices are a key driver of the model, so we'll do some fossil fuel price scenarios. But we don't have a formal understanding then of how those fossil fuel prices interact with other parameters. So I maintain that global sensitivity analysis can give us many more insights into this and could help us create better scenarios, and also or more interesting scenarios, and better explore the model output space. Any questions on that so far? Has anyone any of the modelers here, have you ever created a scenario that's no different from the original scenario you're working from? No? Okay, well, I've done that before. So created a sort of reference scenario and then changed a bunch of parameters in the model to create another scenario, and the results were exactly the same. So that kind of, this kind of activity could have been reduced by understanding which were the key drivers of the model. Okay, so there are a number of different methods for conducting a global sensitivity analysis. Today we're going to focus on variance-based approaches. So these basically compute the proportion of the variance in the output that's explained by variation in the input. And we can compute the first order effects. So that's the direct effect that changing a parameter over its range would have, an input parameter over its range would have on the output that you're looking at. And you can also compute total order effects. So this is the sum of the direct and interaction effects for each input. And you can also recover then this the nonlinear and interaction effects on the model output. So the disadvantage of these variance-based approaches is that while they give you lots of insights, so you'll understand how, and you'll be able to quantify how model inputs interact with one another, they require a large number of model runs. So you can see this is, you need at least 500 model runs to get some decent results. And K is the number of parameters. That's 500 times the number of input parameters that you're perturbing. So for most energy system models, this isn't really feasible, because even if you have a sort of a couple of minute run times, then that's not possible. However, there are more efficient methods. So, for example, the method of Morris, which is what we're going to use today, that dramatically lowers the computational requirements to sort of 10 times the number of model parameters. And what that does is it basically does a local sensitivity analysis multiple times while changing the values of all of the other parameters. And so this is basically, yeah, as it says, it computes an average of local derivatives. And that provides an estimate, so it doesn't provide as comprehensive information as some of the more advanced variance-based approaches, but it does a pretty good job, and it's particularly good for identifying parameters that are not influential in the model results. So it's also known as a screening approach, because it allows you to sort of remove the dimensionality or reduce the dimensionality of your model. So one tool, and there are a number of tools available for performing global sensitivity analysis, and I'm a co-author developer of the Python library ECELib. So this is a very popular sensitivity analysis library. It's used a lot and embedded in a number of other Python libraries. and it implements some of the methods shown on the screen, which I'm not going to go into, but there are the purpose of the library basically is to make available these very powerful global sensitivity analysis methods and basically save you time. So you don't need to dive into the papers and then try and come up with an implementation of these methods yourself. You can just pick up ECELib and do what you want to do, which is to create a sample, run your model a bunch of times, and then analyze those outputs. So very quickly then, to use the ECELib library, you first define what's called a problem spec. So this is basically essentially a dictionary containing the information about your model. So in this case, we've got 3 parameters named x1, 2, and 3. Those parameters have the bounds of pi, and negative pi as the lower bound and positive pi as the upper bound. And then there's one output produced by the model. Then create a sample. So in this case, we're using the Saltelli sampler, and we run 1024 model runs. And in this case, we're going to calculate the interaction effects as well. So how 2 parameters interact with one another. And then we run our model very many times. In this case, we're using a test model called Ishigami. So this is basically an invented model which is very difficult for global sensitivity analysis methods to evaluate. And then we run the matching method for the Saltelli sampler. We analyze it using the Sobol analysis. And this then produces results. So we've got 3 parameters. We've performed a number of different evaluations of the model for one output, and we can see the total order. So the total effect, basically a total influence of these individual parameters with some confidence intervals, and then the first order effect, and then the interaction effects are also quantified. So you can see the interactions between x1 and x2 have this size, x1 and x3, and x2 and x3 are very small. And we can also plot these, so that's easier to see. So this test Ishigami function is very tricky because the total order effects of the parameters of x1, x2, and x3 are designed to decline like this. However, the first order effects increase, but for the third parameter is 0, and then there are very high interaction effects between the first and the third parameter. Does everyone understand what I say when I mean an interaction effect? Does anyone not understand? Any virtual nods? Okay, well, an interaction effect is when it's like a multiplicative effect. So it's when one variable influences whether another variable has any effect on the model output. So you could think of it like a switch. So when one variable passes a certain threshold, then that sort of switches another parameter on. In an energy system model, you could think about it like the constraint on the availability of a technology. So it could be if the constraint is 0, then you can't build any of that technology. But as soon as the constraint is relaxed with a positive value, then that technology is available. Yep. So thanks, Yuha, for responding in the chat. Do feel free to write in the chat if you have any questions, and either Trevor and I can pick those up. Okay. So to continue. So yeah, that was a.
Can I ask a question? Can I ask a question quickly?
Please do. Yeah.
Is there any particular advantage to using Sobol indices, let's say, as opposed to Shapley values or something like that?
So I don't know those specific. I know Sobel indices, but I'm not familiar with Shapley values.
So
But
the Shapley value, as far as I remember, it's supposed to, I mean, more or less do the same thing, but the interpretation is it gives you the percentage of the variance in your output that is explained by the variation of each of your input, and it includes, I guess one thing that it does do is that it always includes direct and indirect effects, so you can't do the same decomposition. I guess that might be one disadvantage. On the other hand, I guess it's maybe easier to interpret because they sum to one, their percentages.
Yeah, that sounds very very familiar, very similar. Sorry. Yeah, there are basically a whole bunch of methods that do similar things, and they differ often in various dimensions. So the first way they differ is computational demands, and there's generally a relation between the higher computationally demanding methods give you more information. They also differ in whether you need to run a sample, you need to generate a sample first and then use the matching method to do the analysis. Some of the methods allow you to use whatever results that you have. So if you've done a Monte Carlo analysis, or you've already sort of run your model a lot, there are methods that exist that allow you to just use that given data that you already have. Yeah, I think those are the main differences. Well, so there's a question from David. Was the fact that total effects decrease a feature of the model or the analysis method? That's a feature of the model. Yeah. Yeah. So this is this sort of toy example is just a test function basically to try and really stretch these global sensitivity analysis methods. Okay, so there's a few references. So there's the Saltelli book, Global Sensitivity Analysis, the primer. So that's a good place to start. And then there's a reference for the SALib library and another paper that we've written about its continuing development. So in the Jupyter Notebook. So this slideshow is built off the Jupyter Notebook, which is linked in the session description. So feel free to open that. If you go back to the skills workshop description in the agenda, that you should see a link that Eduardo has posted there. And you can follow along if you like, or you can just watch the slideshow. But I'll take us through this first example. So in the first example, we will basically build this very simple model and then perform a local sensitivity analysis. So we basically want to set the baseline as well. What information do you get from doing a local sensitivity analysis, and then what's the cost of that? So we're starting off with the simplest energy system model you can possibly think of. So you have one resource, one conversion or transformation plant, and one demand. So in this case, we're mining uranium. We've got a nuclear power plant which produces electricity, and we're assuming that the nuclear plant can follow the electricity load profile. So we're making a lot of assumptions in this model, but the aim is just to really demonstrate the approach.
You're muted again for some reason.
Apologies. So we're adding data for capital costs, fixed costs, variable costs, efficiency, operational life, and demand. And then the main assumptions are that we've got a model horizon of 50 years. We've got 8 equal time slices per year, and demand increases linearly. So we'd expect to see a sort of increasing investment in, or continuing investment in the power plant over time. So if we then run this model, we get an objective value. So it builds a lot of costs, a lot of money, and but then we want to actually work out what the sensitivity of the model is to two parameters. These are the parameters that we change. We change the capital costs value and the variable costs, and then we end up with a bunch of different objective values. So in the background, we're using the osmosis model, and this is a least cost optimization model. So in each time step, it seeks to meet the demand for electricity, and to do that, it needs to operate power plants. And if the required capacity is not available to meet that demand, then it will invest in new capacity. And so that's why the objective cost increases or decreases as we change the capital costs and the variable costs, because it has to build and operate these plants. And then what we can do is plot those values. So you see we've run 10 model runs. Each of these dots represents a model run, and we ran 5 model runs. So that's 6, isn't it? 6 model runs, changing the capital cost over a particular range from $2,500 to $5,000 million per gigawatt, and we change the variable cost over a different range, $1.5 million per petajoule to $4 million per petajoule. So can anyone interpret these results? What's going on here? Which of these parameters is more influential? Feel free to shout out.
Potentially, I guess, on the capital cost, since a difference in capital cost has a bigger difference on objective value.
Yeah, exactly. So we basically look at the gradient of the line. So we see that over the range. Yep. So we've got a few responses agreeing in the chat as well. So yeah, the capital cost has the greater influence on the objective function when we change the capital cost over this range. And I guess this makes one important point, is that the results of the sensitivity analysis are contingent on the range over which you're perturbing your inputs. So the main assumption you make then when you're doing a sensitivity analysis is defining this range. So what's the sort of plausible range over which your model parameters could vary? And then this comes back to this idea that, well, you need to then do some kind of assessment of the plausible ranges of these input values, and raises other questions then about how you're considering uncertainty in your analysis. So a few disadvantages then of this approach. So it gives you limited insights into the influence of the parameters. So we saw on the plot that a steeper gradient shows which one is more influential, but you can imagine that as you do this for more and more parameters, then it just becomes very unwieldy. You could plot these parameters all on the same graph if you sort of indexed the values, but then you lose that useful information actually about the relationship between the inputs and the outputs. You also miss interaction effects. So in this example, we're just moving one parameter at a time. We're doing a one at a time sensitivity analysis. And so while it would show non-linear effects in the output and in response to the input, we don't see any interaction effects because we're not moving parameters at the same time. And later we show that if you look at variable costs and efficiency parameters together, then you do see interaction effects in an energy system model. And if you think about how an energy system model is structured, there are lots of interaction effects within that model. And you also get lots of non-linear behaviors from the output of an energy system model. The other disadvantage is that the computational expense here is quite high. So the approach is inefficient. We need to run one model run per step, per individual parameter. Yeah, so that basically takes us through local sensitivity analysis. So this is what we want to move away from. And this is often what we do. A local sensitivity analysis is what we do when we do a sensitivity scenario, right? So we're doing a scenario analysis, and we're like, okay, I've done a high fossil fuel price scenario. I wonder what happens if cars are more efficient, and then we'll change that one parameter and look at those results. So that is in essence a one at a time sensitivity analysis, and the result is that we really explore a very small fraction of the input space. So now we're going to employ a global sensitivity analysis method using the method of Morris. So again, we're keeping with our ridiculously simple energy system model, and in this we need to do a workflow. So we've implemented a workflow to help reduce these errors with handling data. There are three main steps. Firstly, we need to sort of configure the workflow. Then we need to run it, and then we need to interpret the results. And that basically looks like this. So we configure the sensitivity analysis. We tell the sensitivity analysis algorithm how many samples to produce and how many inputs of the model that we're changing the values for. But we then send that into the workflow, and it generates all of the model runs for us. And then we bring those all together and analyze the sample against the model results to generate these sensitivity indices. So the configuration file basically contains parameters that define how the sensitivity analysis will be conducted. This takes us on to one sort of implementation challenge, I guess, within energy system models, and one thing that's a bit annoying, or that requires some thinking about. So in a sensitivity analysis, we can define sort of one parameter, but often in an energy system model, we're defining parameters over time, and we need to come up with a way to then translate the sensitivity parameter, or the input parameter, to the model into a time series. Trevor's been thinking about this a lot, and we came up with a number of different ways of representing different values. So one is just to have a fixed start and end point, and in this case you wouldn't do a sensitivity analysis at all. You're just keeping the value stationary. Or you might keep the value the same throughout the model horizon, but you want to increase or decrease that value. And the way we specify that in the configuration file, which you'll play with in a minute, is you specify the sort of top and bottom values, and then those are interpolated in a straight line at the same value through over the years. And then you might have a factor which changes over time, so a time-dependent factor. And again, the simplest example is if you keep that fixed, but it's an increasing value over time. Or you might fix just the start point, and you'd allow the end point to vary, or you'd allow both the beginning and the end point of the value of the parameter vary. And we make the assumption that we just do a straight line interpolation between these 2 points, but this could be extended in the future. So this is a sort of implementation detail, which is particular, I guess, to energy system models, and it addresses the challenge of how to go from the sampled value, which is one number, into a parameter which is meaningful for an energy system model which is defined over time. So this could be energy demand, for example. You'd want to vary energy demand in the near term and in the long term, and you'd want to investigate in your sensitivity analysis the influence of energy demand on total system cost. So you'd use this sort of third approach, or you might use this second one. So now we're sort of diving into this. So I'm gonna go through quickly and not dwell on this too much. But there are a few sort of I guess details about how to parameterize our fairly ugly configuration file. So you'll be doing this in a minute. And then we'd run the workflow. So behind the Jupyter Notebook, which you have access to, there's a snakemake workflow. And this sort of hack here manages to make it work. So this basically tells the Jupyter Notebook to run snakemake on the command line. And we'll first clean the workflow, so that deletes any existing files, and then we run it. And you'll see that to do this, there are about 145 separate tasks to do the sensitivity analysis in this workflow. One of the constraints with running the Jupyter Notebook on Binder, so running this in the browser, is that there's only one core available on the machine. So even this very trivial example is going to take quite a while to run. So just be patient. You might want to start running it now, and we'll look at the results together. And then we can look at the results. So after you've run the workflow, and we'll just go through these together. So the method of Morris computes this sort of the method of Morris does this sort of local sensitivity analysis. It computes the derivative of the model at different points in the input space, and so it's very it makes a sort of clever sample where the parameter values are changed in a particular order in different combinations. So it then computes these gradients, and then it averages those gradients for each of the parameters while changing all of the other input values. The result is that you get a pretty good estimate of which of the parameters are influential and which are not. But what you get out of that approach are these indicators. So the mu value estimates the mean of the distribution of the elementary effects of the derivatives, if you like. The mu star estimates the mean of the absolute elementary effects. So it basically does an absolute transformation of the elementary effects, and that's useful if you have effects that are both positive and negative when a parameter changes over its range. And then sigma provides an indication of the non-linear effects or the interaction with other factors. So I think the method of Morris is reasonably intuitive to understand. There's the papers written on it are pretty clear, and this is what the results look like. So one thing to notice is that results are in the same unit as the output parameter that we're doing the sensitivity analysis for. So in this case, we're looking at the total system cost, and so you can see quite clearly then that we have a ranking of these different inputs, and then we can plot that in a chart as well. So the results here show that the capital cost of this nuclear power plant is clearly the most influential parameter. And then, so IAR is basically the inverse efficiency of the plant. So this is the input activity ratio. So that's a osmosis specific parameter. And then variable means the variable cost of the fuel, essentially. So this is the fuel cost. So these two lines here show the value of sigma, and that's why the corresponding dots on the plot are further up the y-axis here. And they show that there is a small interaction effect then between the efficiency of the plant and the variable costs. And so that's hopefully fairly intuitive. If you need more fuel, then the cost of the fuel and the cost of the fuel increases, then you'll have a higher effect on the total cost than if you had a very efficient plant and fuel is cheap. So those two factors interact. Okay, I'll just pause there. Are there any questions on that? Did I make sense? Trevor, do you have anything to add? Was there anything that I wasn't clear on that you think I missed?
No, I think you've covered everything great so far.
Okay.
There's a question in the chat.
Yeah. Okay. So so Yuha, yeah. So that first example was a local sensitivity analysis. So I hope that that's clear now. How would you vary time series like capacity factor? So in a non-linear way. Yeah. So at the moment, this is an implementation detail basically. So at the moment, we're just doing a linear interpolation between two values, but technically we could define any function. It's just a matter of having the time and the energy to do that. Our focus at the moment has just been on trying to get the global sensitivity analysis up and running and seeing this. But you could define your own sort of custom function for how parameters change over time. The other way is that you could define multiple parameters to define function shapes and include those in your global sensitivity analysis if you wanted to. And then Emir has a question: could it be normalized to a higher or lower average capacity factor?
Just as a quick comment on Yuha's previous one.
Right.
Yeah.
Yeah. Yeah. Okay. Great. Okay. So so now it's over to you. We're going to move to the Jupyter Notebook, which looks like this. I think Trevor pasted the link to the binder, yeah, in the chat as well. So it might take a few seconds for that to pick up. So David asks, is sigma the interaction with all other parameters? Right, yeah. So in the method of Morris, David, the sigma value sort of bundles up a number of things into one. So it tells you that a parameter is either non-linear and or it interacts with other parameters. So it doesn't tell you anything about which other parameters it interacts with. However, that is a feature of the first approach I showed you when I used the test function. So if you use a Sobol analysis, then you can get second and higher order effects. So you'll see, then you'll identify pairs of variables that interact with one another, and you'll quantify the magnitude of that interaction. And you'd be able to compare that then with the direct effect of the individual parameters. So basically in the Jupyter Notebook, you'll see everything, actually a bit more than what I just presented. So if you scroll down, so all of the information I've shown there is available in the Jupyter Notebook. It might look a bit different on the binder because I'm running this locally. But if you scroll down, sorry, I should say, yeah, if you scroll all the way down to example 2, down. So here we go. Oh no, sorry, we're going to start example 3, aren't we? Yeah, so if you just click on one of the cells, and then you should, in the cell menu, be able to run all above. So basically, if you've never used a Jupyter Notebook before, this is an interactive Python environment, which is available in your web browser. And what you're looking at is a Jupyter Notebook on binder hub. So basically, Trevor and I have set this up and published it, and now you can access it anywhere on the internet. So behind the Jupyter Notebook, in the Jupyter Notebook, there are different cells. There are cells containing text, which you can't run, but then there are also code cells as well. And in those code cells, we can write some scripts and call Python functions and just write code as pretty much as per normal. And you need to run those cells in a particular order to get the code at the bottom to work. So you can just click on Run All Above. And that the notebook will then tick through each of those cells. When the cell is waiting to run, then it has a star. And when it's completed running, you'll be able to see a number. So you see, be able to then follow the order of the running of the code. So this will remain online, and you'll be able to view it in the future, and come back to it if you're interested in picking this up again. Okay, so you can see that it's just running the SnakeMake workflow for example 2 now, and it will take a bit of time. Right, so on to example 3. So in this example, it's now up to you to modify the sensitivity parameters. So we've left a bit of work for you to do. So the first step is to modify the configuration file. And you can do that just by clicking on this link, and that will open another window containing a very ugly looking text file, which is how you parameterize the sensitivity analysis. So each row is basically a different parameter relating to our osmosis model. So here we're define a range for capital cost, fixed cost, for variable cost, for the demand, for the input activity ratio, which is like this inverse efficiency, and the operational life of the plant. So how long it's available before the plant's decommissioned, and then the model looking to invest in a new plant. So I've already filled out some values here. I guess the information you don't have is the units. And Trevor, I was hoping actually you could fill us in on what sort of magnitude should we be of value should we be using for these inputs. Because I got some pretty strange values when I ran my test.
Sure, let me just find some in 2 seconds.
So the work for you to do, then if you're participating, is to fill out this file. And so there are 4 main columns that correspond to the starts and endpoints of the parameters. So using these first 2 columns, which are going to be very difficult to view below. I'm afraid I'm sorry, this is just what we have to deal with. So in these first 2 columns, you define the minimum and the maximum range for the first year. And in the next 2 columns, you define the minimum and maximum range for the end year. And then the values are interpolated between those. So they're first sampled between the minimum and maximum, and then interpolated according to those different options we defined earlier. Then once you've done that, you can then run the workflow, and you can do that by clicking in this in the cell, and you can click the Run button, or you can just press Shift and Enter, and then you need to do that on this one, and then below it. Okay, yeah, question from you. How about probability distributions? Yep, you can assign, so SALib allows you to define probability distributions for the inputs, so then it samples from the distribution rather than a uniform distribution. How can you should be able to, right, yeah, so you've opened the parameters file, but you're unable to edit it on Binder. Yeah, So what you need to do is in the file tree, you need to right click and then open with editor. Let me just open the binder link and I'll show you. If you're confident in using Python and Jupyter Notebook, you're also welcome to get the code off the GitHub repository and then run this locally, and that will obviously be a lot quicker than using the cloud computer infrastructure provided by Binder. Okay, so this is what you see when you open the file on Bind. So let's scroll down to exercise 3, example 3. So what happened was if you click on the link in here, the file should open in Editor. No, it doesn't seem to work. Okay, so what you can do is look in examples here. Example 3, and then you need to right click and open with editor, and that should allow you then to edit this file. Yep. So a question from Roberto: How do we select the maximum and minimum values? Do you use your own expertise, or do you elicit expert opinions, or do you do a literature review, or how do you do that? That's a good question. I think you use all of those approaches. It depends also on what you're doing the sensitivity analysis for. So if you're doing this as part of your model development, which I'd strongly recommend doing, then perhaps it doesn't matter quite so much the particular ranges of values that you specify. But you'd want to use, I think to start with, you'd want to use really the sort of maximum plausible ranges of values for the inputs. The aim really is to and one advantage of doing a sensitivity analysis is you stretch the model, so you really push it to areas of the input space that maybe you wouldn't normally consider, and that's a useful exercise. And I'm not sure if you saw the presentations yesterday in the ECEMF session, but that's what we've been doing in that project on using a different approach, but using diagnostic scenarios. So really trying to push the models involved in that project into very bizarre situations, just to see how the models themselves react. So if you do this then as part of the process of model development, you're already sort of prepared for those situations where you need to explore a part of the model input space that's perhaps quite unusual, and avoid those situations of getting very, very strange results or behavior.
Πες ότι αν είναι 100 χιλιόμετρα, 80 χιλιόμετρα την ημέρα το χειμώνα, τα μισά, σημαίνει 40.
Okay, so Trevor's written in the chat how to modify this parameters file. Great, so I'll follow along and do the same. Okay, so I think nuclear is going to get a lot cheaper, so I'm gonna put it to $1,000 million per. I guess that's $1 billion per gigawatt, because these are in $1 million per gigawatt. So fixed cost. So these should be okay. Yeah, I don't have any. Okay, from that. So variable cost. Right, specified annual demand. So this should be in the region of sort of tens of thousands. I'm pretty sure what the current annual demand is, but I think future energy demand could stay the same or it could double. So I'm going to explore a wide range in the future. Impact activity ratio. Yeah, I don't think that's going to change much. Yeah, slightly. Okay, so I'm happy with my parameter file now. I've sort of changed the values. So in the first year, I think capital cost for nuclear is going to be between $4.5 and $5.5 billion per gigawatt. But over time, it's going to decrease in cost. It might get very, very cheap, or it might stay but in any case, it's going to decrease in cost. That's my very subjective beliefs for the purpose of this this workshop. So now I'm going to go back and I'm going to cheat because I've got 8 cores, so I'm going to use those and run this. So I just press Shift and Enter to run the workflow. And now that snake workflow is going to run in the background and hopefully solve or produce some sensitivity analysis results. So while that's just going to tick away, see all the scenarios being solved. So any more questions? You managed to get the, looks like I've got some results. Okay, interesting. Okay, so these are the results from then looking at these 6 parameters now input to the super simple model. And here we see that the magnitude or the size of the blue bars represent how influential that parameter is. So you can see that demand seems to be the most important parameter. That intuitively makes sense. As the demand increases, then the size of the supply needs to increase, and that requires investment, so that will increase the size of the magnitude of the total cost, which is what we're measuring here. The capital cost of the plant is also influential, but not as much as the demand I specified. So remember, I specified quite a wide range for demand doubling with the current values. The operational life is also quite influential, and I guess that's because with a shorter operational life, then the model will need to invest more frequently. And then variable cost and fixed cost around the same magnitude, and the efficiency of the plant doesn't seem to have very much effect at all. And then all of the parameters seem to interact, and we can maybe try and think about why there are interaction effects. Would anyone online like to think about why there might be interaction effects between demand and other parameters? What would demand interact with? Yeah, so demand interacts with increased demand, increased production. Yeah, exactly. So demand requires a bigger supply side, but then if that supply side is more expensive, then those two factors will interact with one another. So there are probably multiplicative effects between demand, capital, cost of the nuclear power plant, and then with all of the other parameters as well. Yep. So Nandi says agrees. Demand would interact with capital cost, variable cost, and fixed cost. Yeah. So obviously this has been a super simple model, very, very simple example, with just one technology and one demand and one resource. In the paper, we've explored more complicated and more realistic energy system models, and we've done so in a sort of step-by-step way, which describes how you can then relate the insights you get from the global sensitivity analysis to the behavior of energy system models and what information that can tell you. So we hope that will be a useful contribution to the community. We've got about 20 minutes left, so I'll leave the session open. But I don't have any more material to share, so I can do a sort of wrap up. So basically, in the skills workshop, we've explored how we apply a global sensitivity analysis approach to this super simple model, and we compared that with a local sensitivity analysis where we just perturb one input at a time. And we've shown that while that gives some basic insights, we don't get any insights about interaction effects. And it's also quite computationally inefficient. We're having to run the model quite a lot of times just to get information about 2 parameters. So what we've done is applied one particular approach, the method of Morris, to a simple example of an energy system model. And we've shown that more efficiently than the one at a time of approach, you can get many more insights. So while it was very slow to run on the binder, due to the limitations of the cloud computer. Basically, to get all of this information, we were running just 35 model runs. So so that scales quite nicely. The method of Morris also allows you to group parameters together, so you can further increase the computational, the trade-off between computational efficiency and insights. So we looked at the sensitivity of one output, which was total discounted cost, but basically you can perform a sensitivity analysis on any of the model outputs. So, and you wouldn't need to do any more model runs to do this. So we could have performed the analysis step of our sensitivity analysis on, say, emissions, on installed capacity of renewables, basically any output that you get from the model. And you'll then identify what are the influential or non-influential parameters for those particular outputs. And that, of course, could change, those results could change quite significantly, depending on whether you're comparing that with total cost or with emissions and so on. And then we've used the method of Morris, and that gives us this sort of basic level of information. And I think that's sort of good enough. It's treads this line really well between computational efficiency and the type of information you get from applying it to the model. But there are many sort of much more powerful approaches that allow you to really quantify these sort of first, second, and higher order interactions between parameters. So if you do have a simpler model than an energy system optimization model, then you can apply these approaches, and the sensitivity analysis library ECELIB allows you to do that very straightforwardly. So yeah, that's all I have for today. So you're welcome to stay in the room and keep playing with the sensitivity analysis, and I'll be online for the next 15 minutes to answer any questions you have.
Thank you for the presentation. I'll ask a little question about the scalability of the methods. I'm more of IM modeler rather than an energy system modeler. And has anyone ever considered applying global system analysis on integrated assessment model, or just more large scale energy models?
Hi, Thibaut. Yeah, so people have applied global sensitivity analysis methods to integrated assessment models. I can find some references for you, actually. I'll do that and paste them in the chat. So I think some people working on the image model have done global sensitivity analysis of modules of image, and I think, yeah, anyway, I'll have a look. I'll have a look for the references. Obviously, those models are generally more computationally demanding than an energy system model, and the approaches used often simpler. So there is a method, oops, I think it's called fractional factorial. If we go to the list of methods again. Yeah, so this fractional factorial sensitivity analysis. So this is very computationally cheap, but it gives limited insights. So basically what you do is you perturb inputs between 2 points, so the extreme points of their range, and then explore combinations of those. So that gives you some indication of then influence, but you obviously miss out on insights about what happens in the middle of the parameters range and non-linearities and yeah, other types of information.
Can I ask another question? So, if I understood correctly, the method you showed basically for a given number of parameters, the number of model evaluations that you do is fixed, right?
The number of model evaluations scales according to the number of parameters.
So
But
it's
yeah.
10 times k plus 2.
Yeah.
Now, what I have been wondering is, if you have a given number of model evaluations for a given number of parameters, does the information that you get from this method not become sort of potentially less accurate the more rugged is the response surface of your model? Because you're doing basically partial derivatives at a fixed number of different points. And, you know, are there, in consequence of that, are there any methods that somehow try to take this into account?
Could you just repeat that, Severin, so I can get my head around your question
sure.
again?
So, well, you do basically a fixed number of model evaluations at different points of the response surface of your model, and calculate partial derivatives, right? But imagine that you have a model with sort of a very rugged response surface, so that you know, the partial derivatives are extremely different at various different points. So I would guess that the more rugged the response surface of your model is, the less reliable this method becomes. Would be my guess. And my question would be if you are aware of any methods that sort of try to take this into account.
Right.
Meaning
Yeah.
the more rugged is the response surface, the more model evaluations you will do.
Yeah. Thanks. That's a very clear description. Yeah. So I think the method of Morris would not be a good approach, because not only are you taking relatively few measurements, but you would also then average those measurements out. So if you were lucky enough to get one very high partial derivative value, that would then be sort of averaged out by all of the other ones in that particular parameter. So you'd sort of miss that information. You'll get a reasonable estimate of the influence of the parameter, but you may be what you would get is a measure of the sigma value on the method of Morris gives you a measure of the standard deviation of those gradients that it does measure. So you'll get some insights or understanding that, okay, there's something going on here. There's either an interaction effect or some responses of these parameter values that are there's differences in the partial derivatives that are calculated. If you used an approach like Sobol, then firstly you'll be doing many more measurements, so you'll get a more accurate picture, but you're still only looking at it's still a variance-based approach, right? So you're looking at the variation in the output that's attributable to each input, and you're not really measuring anything about the roughness of the response. So I think it's more the approach in general that would be the issue. So you'd want to look at a different class of sensitivity analysis approaches, probably.
Okay.
But yeah, I don't have any more useful information than that, I'm afraid.
Yeah, fair enough. It's just basically because, in my experience, for instance, agent-based models, sometimes this stuff can be a mess because response surfaces can be quite chaotic.
Η οποία λέει εδώ ότι, ναι, 45-08-44.
But yeah, thank you.
Yeah, thanks for the question, Severin.
I will. I'm thinking again about the question before regarding the capacity factors, and was just wondering if you have any experience in like how one could do that in the analysis, and in the energy systems model, I would consider them quite influential. So, are there any efficient methods that you have already used?
So you mean in terms of including them in a sensitivity analysis?
Yeah, exactly. So since yeah, I right now have a model where for some reason offshore wind is phased out because the model goes into onshore wind. So, and I assume that that might have something to do with the cost to capacity factor ratio. So vice versa. So it's like in that sense, it would be very interesting to see where it's kind of the tipping point of the model, where it goes from onshore to offshore.
In that case, you're in this sort of factor mapping setting, right? So it's slightly different to what we've been talking about today. So if you're trying to identify the values, the sort of threshold effect of input parameter values that cause a particular output in the model or a particular behavior, you'd want to use this factor mapping setting. And that's, so there are similar approaches, or maybe appropriate approaches in the scenario discovery, so sort of area of the literature. So you could use one of the algorithms like Prim or CART, for example, to identify the link between that interesting part of the output space and try and work out what threshold effects. What are the values of the input parameters that cause that? If you just want to do a sensitivity analysis, so a sensitivity analysis would tell you that there was some interaction between capacity factor and the capital cost, it probably wouldn't give you that much insight into individual technologies. I think one interesting thing we're seeing, and very intuitive result we're seeing from the more complicated implementation of the energy system model with the global sensitivity analysis, is when you have a whole bunch of technologies, then essentially they just compete against one another. So often people play with the capital costs, right? They'll do a different scenarios of different capital costs of technologies. But what we see in the global sensitivity analysis is that all that does really is just rearrange the supply cost curve for technologies. So it doesn't influence the total energy system cost very much at all, because the optimization model would just choose the next, the cheapest technology to meet demand. And you might get the same thing if you're just playing with the capacity factors. Then the model will just switch to the next available technology that's more economically or more cost effective.
Yeah, that makes sense.
Just a comment on that, kind of also clarifying to myself, but also maybe continuing that discussion, is that what I got from Will's previous answer to that capacity factor question is that you could, for instance, have a create time series for different capacity factors. So you would have a 28% capacity factor time series and then 29% capacity factor time series, which of course they change non-linearly when you go from 28 to 29, but you could then use these sets of capacity factor time series to sample from those sets as a part of your sampling for the global sensitivity analysis, right?
Yeah, so in running the sensitivity analysis, you would, sorry, I was writing a response to someone else, so I didn't, forgive me if I don't answer this correctly, but when we were running the sensitivity analysis, the sampling approach basically would create a new time series for the capacity factor for each of the model runs. So, and would then solve the model given that information. And the sensitivity analysis would then tell you, well, how influential that capacity factor parameter was relative to all of the other parameters that you're looking at.
Yeah, right. And I was just meaning that you probably need to pre-calculate those time series because it's a more complicated thing than just scaling or something. So you need to have a pre-made set of capacity factor time series.
Yeah, exactly. And you could definitely implement that fairly easily with a lookup table or some of them, or you just write a formula to replace the straight line interpolation that we're currently using.
And also a comment to that offshore onshore thing. In our runs, it typically never switches over very quickly because there is a benefit of having different time series, and therefore, even if one of them is lower cost, it still wants to build both because there is a system value in having that diversity in time series. But of course, at some point, it's just too expensive.
Great. So Thibault, I've pasted a few abbreviated references in the chat. I hope that'll be good enough for you to find the papers. If not, then you can just send me an email, and I can send those to you. Okay, I think that wraps up our session, everyone. So many thanks for joining, and yeah, keep in touch. Thanks if you shared your email, and I'll forward you a link to the paper once Trevor and I have submitted it. And yeah, look forward to seeing many more global sensitivity analysis publications in the future. Thanks.